Hey, welcome back to Calculus. In this second video lecture of section 4.3, we're going to take a look at what kind of information the second derivative carries about a function. All right, so in particular, I want to tell you about something called concavity and how to determine the intervals over which a function is concave up and down, what inflection points are and how to find them. And then I want to tell you about something called the second derivative test, which is, well, it's an alternative for the first derivative test. It's got kind of an unfortunate name because it also classifies local extrema, but it does it with the second derivative, not the first derivative. All right, and once again, I'm going to try to convince you that the best way to keep your head straight and organize all this vast amount of information we're talking about is by making sign diagrams. And in this lecture, we'll be making them for both the first and the second derivative. Okay, so I've got already on this screen the definition of what I mean by concave up and concave down. Let's take a look at it. So it says a graph is concave up. I'm going to call the graph concave up if it lies above all of its tangent lines. Yeah, so concave up or concave upward, if when you graph a bunch of tangent line segments on that graph, the graph would be lying above those tangent line segments. And this is always on an interval, just like with the increasing and decreasing. I'm talking about this stuff being true for all input values on some interval I. All right, it's concave down if it's below its graph. Okay, if the graph, you draw a bunch of tangent line segments and the graph is always, you can kind of think of it, it's bending down, reading left to right, it's bending down and away from its tangent lines, then we'll call it concave down. So if it lies below those things. That's a little bit abstract. So let's take a look at some pictures. Okay, so say starting on the top left side here, what do I mean by a graph being concave up? So the function is drawn in blue. It's that curve shape there. And look, if you look at a bunch of its tangent line segments, see how it's kind of bending up and away from its tangent line segments? It's above it, or it's kind of curved up like this, concave up. Likewise, concave down means that the function is bending down and away from its tangent segments. If you like, I could say a graph is concave up if its derivative is increasing, and it's concave down if its derivative is decreasing. Those are equivalent definitions, but I kind of like this geometric flavor. I think this diagram is sort of a nice picture. It's a function that's changing concavity. So again, reading it from left to right, starting at x equals a over here, it's got this nice concave down segment. That's what the CD stands for. I'll use the same acronyms below. So it's concave down from x equals a to x equals b. But then at x equals b, it switches. It becomes concave up until x gets to be equal to c. All right? It's probably a good point to stop and tell you what I mean by an inflection point. An inflection point, by definition, is a point on the graph where the function is changing concavity. Just like with inputs and output, or extrema rather, excuse me, we'll usually specify inflection points by just giving their x values. So I've got an inflection point here at x equals b. Yeah, an inflection point at x equals b because the concavity switched from down to up. There's another inflection point at c. It's subtle because the graph is very straight there, but the concavity is changing from up to down. It changes back to up at d. There's a third inflection point. Yeah. Notice at E, that cusp looks like a point of non-differentiability for this function. So does the x value d, by the way, but there's no inflection point there. It's concave up on the interval up until x is equal to E, and then it's concave up again. So there's no inflection point. The concavity does switch at the x value p. The x value p, the concavity switches. All right, so it's concave down from p to q. All right, so one of the things I want to do in this lecture is, given a function, I'd like to be able to determine the intervals over which it's concave up and concave down, and I'd like to be able to find all those inflection points. And we'll do it by making a sign diagram for the second derivative. And just like with the first derivative in extrema, we'll kind of answer both questions at the same time. So let me scroll up here and show you what I mean by the concavity test. So the concavity test, again, it's very nice. If the second derivative is positive everywhere in your interval, then your function's concave up, okay, on that interval. If the second derivative is identically negative on the interval, then it's concave down. So again, I like this because it kind of fits well in my brain anyway. Positive up, negative down, okay? Let's use it. You might remember this example one polynomial from the previous lecture where we determined where it was increasing and decreasing. Now I want to determine where it's concave up and where it's concave down. Okay, and I'd also like to find the x coordinates of the inflection points. I'd like to say where the concavity switches, if it ever does. And our strategy is to use this concavity test. We're going to make a sign diagram, but we're going to make it for the second derivative. Okay. I've written this example out so we can go a little bit quicker here. We've already computed the first derivative in the previous lecture, but there it is again. Stop the video and verify these calculations. The first derivative of that fourth degree polynomial is this cubic. Differentiate again, and you get that quadratic polynomial. Yeah, 3 times 12 is 36, and so on and so on. I could factor a 12 out of that thing, so here's my second derivative factored, and I am setting that equal to 0. I'm setting it equal to 0 because I want to know where it's positive and negative, so I'll check in between. I tried for a second, I couldn't factor this polynomial, 3x squared minus 2x minus 2. I tried to do the little reverse FOIL thing. I usually try to do that for about that long before I just use the quadratic formula. So I couldn't factor it, so I'm just running it through the old quadratic formula. My a is 3, my b is -2, my c is -2. I won't bore you here with the details of the quadratic formula, but you're welcome to come talk to me in my office hour about it. But there's the computation. There's my two values of x. 1 plus square root of 7 over 3 and 1 minus square root of 7 over 3. Those two values of x make the second derivative 0. So I mark them on my sign diagram. Notice that I've labeled my sign diagram over here with what function it is, f double prime. All right, and then you can check the signs. If you take a number less than this, less than 1 minus square root of 7 over 3, then you'll see that the second derivative there is positive. Another way to see that is the second derivative is an opening up parabola, and an opening up parabola would change from positive to negative back to positive. But anyway, you check the signs. I'm just gonna pass by it, so you can stop the video and check them. But there's my sign diagram for my second derivative, accurately filled in. And now I just interpret it. So f is concave up. The colors will make sense here in a second. Wherever that second derivative is positive. That second derivative is positive from negative infinity up to 1 minus root 7 over 3. And then again from 1 plus root 7 over 3 to infinity. All right. So I've got those two symmetric values about the x-axis. Good. Where's it concave down? It's concave down where the second derivative is negative. So that's between those two numbers, 1 plus and minus square root of 7 over 3. Nice. All right. So we've seen the graph of this function before. We've seen the graph of this function before. I'm just bringing it back here. I should have mentioned this while we were still seeing the sign diagram, that look, the concavity switched from positive to negative at this number, so it's an inflection point. It switched from negative to positive at 1 plus root 7 over 3, so it's also an inflection point. Here are their decimal approximations, if you like them. 1 minus root 7 over 3 and 1 plus root 7 over 3. And now we know in this picture, I'd have to kind of zoom in. I've just marked those numbers there, but those are the precise places where it's kind of easy to see that this thing switches from concave up to down somewhere over there, but where? Where exactly? What is the exact x value where that concavity change happens? It's exactly at 1 minus the square root of 7 over 3. It's approximately minus 0.5. All right, likewise, the concavity switches from up back to down somewhere. Where is that somewhere? It's exactly 1 plus root 7 over 3. All right, approximately 1.2. Nice. So there's what the second derivative carries information about, concavity and where it changes. Nice. Let's do an example. This one I haven't written out, so I'm going to work with you while we're talking. And it's kind of the kitchen sink example. Taking a function, sine of x, I'm restricting its domain to 0 to 2 pi. If we know what happens on 0 to 2 pi, we can kind of reconstruct the whole real line by periodicity. And I want to find everything. I want everything. I want, where's this thing increasing and decreasing? Where are its local extrema and what kind are they? Where's it concave up and where's it concave down? Where's its inflection points? You know all these things probably from the sine function. You took a trigonometry class. You know the sine function's graph well. I'm choosing to do this as example number 2 because I want to show you how the calculus can arrive at those answers. Yeah, and we won't get bogged down in algebra. The algebra of solving, equations equal to 0, it can be difficult. but I want to choose an example where we kind of focus on the structure of the idea. Okay, so let's see what we got to do. To answer all these questions, we need sign diagrams. We need sign diagrams for f prime and f double prime. So this is how I like to organize my work in this stuff. When somebody hands me a problem like this, they ask me for all of this information about a function. First thing I do is quietly calculate and simplify its derivatives. Well, first thing I do is grab a pen, and then I calculate its derivatives. Here I don't really calculate anything. I know the derivative. The derivative of sine is cosine. You know it too. The second derivative, well, that's just the derivative of cosine. That's minus sine. All right, so there's my derivatives, and there's not really any simplification to do because those are just what they are. So then I make sign diagrams. I make sign diagrams. One for f and one for f prime. Right, so I'm going to make two of these things. I'm going to make two of these sign diagrams. If I can line them up. I like to line them up. Why? Because I'm going to be inferring two things about, I'm going to be inferring from both the first derivative and the second derivative. If I knew how to edit videos, I would edit that stumble out, but I'm stuck with it. So one of these sign diagrams is going to be for f, one of them is going to be for f prime, or for f prime, and one's for f double prime. Remember that the domain of this function was restricted. So when we write these intervals, we're going to be capping everything below by 0 and everything above by 2 pi. Okay, so these things are restricted domains. And now we have to fill in the signs. So the first derivative is the cosine function. All right, so just between 0 and 2 pi, where is the cosine function equal to 0? The cosine function is the first coordinate on the unit circle. So that's 0 at pi over 2 and 3 pi over 2, and nowhere else. So I'm going to mark those things about approximately there and there, pi over 2 and 3 pi over 2. Cosine is 0. And from the unit circle, in this first quadrant, right? 0 to pi over 2 is the first quadrant. The cosine is positive there. In quadrants 2 and 3, the cosine is negative, and in quadrant 4, the cosine is positive. You can choose values and use a calculator to do that too, but I'm taking advantage of my unit circle trig. I also need to know when the second derivative is equal to 0. These things are continuous, defined everywhere functions, so the only critical points will be values that make them 0. Minus sine is 0 if and only if sine is, and that happens at 0, pi, and 2 pi. So some endpoints, okay, 0 and 2 pi, and then right in the middle. And now careful, the second derivative is the opposite of the sine function. So from 0 to pi, sine is positive, so its opposite will be negative. From pi to 2 pi, sine is negative, so its opposite will be positive. All right, so there I've got lined up, neatly organized, completely filled in sign diagrams for the first derivative and the second derivative. So I'll scroll back here, but I just want to say that we are in a perfect position if we know our theory, if we know the increasing decreasing test, we know the first derivative test, we know the concavity test, and we know what inflection point means. These two diagrams are going to answer all of that for us. All we have to do now is extract the information from these diagrams. All right, the diagrams, I'm sorry I smashed them so close together. If I could do this again, I would spread those things out a little bit. Okay, so let's start recording our information. I got to leave those diagrams in sight because that's how I'm answering all this stuff. So what do you want to say first? How about f is increasing? Well, it's increasing where the first derivative is positive. Can you pause the video right now and say this before me? It's increasing from 0 to pi over 2, and then again from 3 pi over 2 to 2 pi. And I'm just using open intervals because these are notions about intervals. It doesn't matter about the endpoints. It's irrelevant. Where's f decreasing? Well, it's decreasing where the derivative is negative. So that's pi over 2 to 3 pi over 2. Yeah, it's decreasing from pi over 2 to 3 pi over 2. I hope you guys can't hear the weed eater This is a long video. I'm going to try to keep it short, but good, decreasing on that interval. So where are extrema? I like to come back up here. What color was I using? Let's see, we were increasing and then decreasing. So it looks like we have a local max at pi over 2. We're decreasing and then increasing. We have a local min at 3 pi over 2. Let's write that down. So we have a local maximum at x equals pi over 2. Sign diagram tells me that. We have a local min at x equals 3 pi over 2. Is this sounding familiar about the sine wave? We're going to look at a picture of the sine wave here when we're done. I'll probably just hand sketch one maybe. Okay, what about the concavity? Well, the second derivative tells us that. I'm going to try to leave that sine diagram up there. So f is concave up on what interval? Well, from pi to 2 pi. F is concave down from 0 to pi. And there's one inflection point, and that inflection point is at x equals pi. Okay, so that's how those two sine diagrams answer all of that information. Instead of having some kind of fancy computer-generated picture here, let's just draw a real rough sketch. Well, when I was a calculus student, when we were taught all this material, it was under the guise of like how to draw an accurate graph of a function. Now in the world of Desmos, graphing calculators, machines, graphing, you don't really have to know how to plot things by hand anymore. So what we're learning in here is how to carefully analyze this graph. Yeah, like this is the graph of the sine function. I just drew it on there from at least on its from 0 to 2 pi anyway. And we just learned the exact location of that local maximum. We wrote above that it was at pi over 2. The exact location of this minimum is 3 pi over 2. Yeah. We wrote that the function was increasing on those two intervals. Yeah, from 0 to pi over 2, and then again from 3 pi over 2 to 2 pi. It was decreasing in between. We have the exact values. There's one and only one inflection point, and it happens at x equals pi. Sine of pi is 0. So we know all of this about the sine function, but the point is that you can analyze trickier functions, yeah, things where things look a little bit subtle, and you can find these exact values. So even in our book, it's still written like, well, these are techniques to graph functions. You don't need techniques to graph functions. You have Desmos, you have an internet connection. I hope you do, because you're taking an online class. You can graph a function. You can graph any function. But you might want to know things like, hey, where did that function, exactly where did that function stop climbing and start dropping? You know, maybe in your application, in your field, maybe that's very important to you. You know, maybe you needed to know, I'm just making stuff up now, but maybe the y coordinate of this function is like some, you know, geologic pressure you're interested in some hydrology problem or something, and you need to know as a function of time exactly when did that pressure stop rising and start falling. You know, I don't know, maybe these techniques could be useful for stuff like that. All right, so my plan in this video, well, I am going to say one more thing about this second derivative test. Sorry, I got all carried away and lost my train of thought. But these sine diagrams, there's an alternate way to classify these extrema. Yeah, like looking, let me draw your attention to this critical value, pi over 2. We already analyzed that it was, by the first derivative test, a local maximum. But there's another way to sort of see that. If we take a look at what the concavity is telling us, the concavity is negative at that value. The second derivative tells us that. Negative concavity means the graph looks like this. So we have an extrema. It has to be a local min or a local max. So if it's concave down there, you could say, well, that's got to be a local min, or sorry, excuse me, a local max. If you're concave down at an extrema, you have to be a maximum. Likewise, over here at 3 pi over 2, right? The second derivative is positive, so the graph is concave up there. So that has to be a local min. So the second derivative could have classified those extrema for us. We didn't need these. It's a choice. this first derivative test, which is what I'm saying we didn't need, we could have done it in the green pen. We could have just used the sign diagram for the second derivative. In practice, this choice is not that big of a deal. If you have these two sign diagrams laid out, this is really just sort of an observation. So it's called the second derivative test. And you can see it written here. It's just saying that if you have a critical number, some number that makes your derivative 0, and the second derivative is positive there, then you'd have to have a local minimum. And I was trying to explain that because a positive second derivative means it's concave up. Likewise, negative second derivative means it's concave down. All right, so I have one more example, but this video is probably getting a little bit long, and I'm going to maybe just assume that you can hear the weed eaters too. So I'm going to cut this and then just do this other example in a second video. Who knows, maybe I'll do two more. Okay, so thanks for listening, and sorry about the weed eater.